Have you ever felt like something's missing but you can't quite put your finger on what it is? Well, what if our entire planet feels that way? Imagine vast, continent-sized sections of Earth's foundational material, the very stuff our world is built on, just gone. What if the planet we live on is missing some of its most crucial ingredients right from its very core? It sounds like science fiction, but it's a genuine puzzle that geologists are grappling with today. This is the story of Earth's missing mantle, and the incredible implications it has for everything we know about our world. To understand this mystery, we first need to take a journey deep into the Earth. Forget digging a hole in your backyard. We're talking about going thousands of kilometers down. Beneath the thin crust we live on lies the mantle. It's not a solid, static layer like you might think. Picture a colossal, slow-moving river of hot, semi-molten rock, stretching nearly 3,000 kilometers deep. This isn't just a filler layer. The mantle is the engine of our planet. Its churning, convective currents are what drive plate tectonics, pushing continents around, raising mountain ranges, and triggering earthquakes and volcanic eruptions. It dictates the very shape of our world's surface and has governed its evolution for billions of years. The mantle is fundamental to life as we know it. So, what happens when parts of this vital engine seem to have vanished? Here's where things get really intriguing. For decades, scientists have been studying the chemical makeup of our planet. They do this by analyzing volcanic rocks that originate from deep within the mantle and make their way to the surface. These rocks are like geological messengers, carrying clues about the composition of Earth's interior. By comparing the chemical signatures of these rocks to meteorites, which are believed to represent the primordial building blocks of our solar system, scientists can build a picture of what Earth should be made of. And for a long time, the model seemed to work. The numbers mostly added up. But then, a glaring discrepancy appeared. When scientists started looking closely at certain elements, specifically a group called the moderately volatile elements, things didn't match. Think of elements like zinc, lead, and indium. They aren't as light as gases that escape easily, but they vaporize at lower temperatures than the rocky elements that make up the bulk of the Earth. According to our best models of planet formation, Earth should have a certain amount of these elements mixed into its mantle. Yet, when we analyze mantle-derived rocks, we find significantly less than we expect. It's as if someone baked a planetary cake but forgot to add a huge portion of some key ingredients. We're talking about a deficit of up to 40% for some elements. So the billion-dollar question is, where did it all go? This is the speculative, mind-bending concept of the missing mantle material. It's not just a small rounding error. It's a massive planetary-scale conundrum. Several wild theories have emerged to explain this. One of the most captivating ideas is that this material was never incorporated into the Earth in the first place. Imagine the early solar system, a chaotic construction zone of dust and gas. As the proto-Earth was forming, a period of intense heat and radiation from the young sun could have literally boiled away these more volatile elements from the building blocks before they could fully clump together to form our planet. In this scenario, Earth was born with a fundamental deficit, starting its life with a different chemical recipe than we thought. But another, perhaps even more dramatic theory suggests the material was here, but was violently stripped away. Picture this: a young, still molten Earth in the chaotic aftermath of its formation. A colossal impact, perhaps the very same one that is thought to have created our moon, slams into our planet. The energy of this collision would have been unimaginable, creating a temporary atmosphere of vaporized rock. In this superheated vapor, the more volatile elements would have been preferentially lost, blasted away into space before they had a chance to condense and sink back into the mantle. This collisional erosion theory paints a picture of a traumatic, violent youth for our planet, one that fundamentally altered its composition forever.